Alright, hello everyone. Today we're just going to be going over some specialist mathematics problems relating to trigonometry. So year 11 WACE, specialist trigonometry. So these are some exam level questions. I'm just gonna go through and solve and sort of explain my thinking and what I like to do. Okay, so this is calculator free, so we simply cannot just plug this into graphing calculator and get the answer given to us. We sort of have to think a little bit. So what I like to do is instantly, I just want to write this in terms of an easier function, namely the cosine, just by using the definition of the secant. I want to simplify this a bit further. We can see that this is going to be the cosine, but moved to the right by pi units. So rather than starting here, we're going to be starting here. And then let's say that 5 is the amplitude, just for the sake of example. It should be looking something like this. Or, yeah, something like this. And we can see here that this is precisely the negative cos of x, right? Because the cos of x, I drew this horribly, but it should be like here. The cos of x is going to be something like this, right? I'm going to start here, and then go down here, and then here, and then up here. So we can see that if we move the cosine right by pi, we're pretty much getting the negative of it. We're sort of, moving that far away. A more concrete way of seeing this, a way that I prefer, is just by using the angle sum formula for the cosine. So this means that the cosine of x minus pi is just going to be the cos of x times the cos of pi plus the sine of x sine of pi. Now we can look at the unit circle, and if we think about rotating pi radians, we're going to be at this point here. So the cosine is a horizontal component, which means that this is the cos of x times minus 1. And since we're purely horizontal, there's no vertical, then the sine is simply 0 of pi. So therefore this is 0. So therefore this is equal to negative cos of x, verifying our transformation thinking, or functional transformation thinking. Now that we've sort of written this in a really simple way, we can now begin plotting it. So since this is a rational function with a varying denominator, we have to be careful for when this denominator might be equal to 0. So in other words, we're going to have vertical asymptotes whenever the cosine is equal to 0. Now, since the cosine is a horizontal component of like the unit circle, we know that the cosine is going to be 0 at these two purely vertical points, right? Which is pi half radians and then 3 pi half radians. So we can draw our vertical asymptotes here, something like this here, and then at 3 pi halves here. Okay. Now the asymptotes are really useful in sort of thinking about how the reciprocal trigonometric functions behave. Normally they shoot up to infinity when they approach it. It would normally be like this because if we remember that the negative cosine, what we have before, is purely positive in this like part here, right? Here the amplitude is just scaled up just so you can see it, but this is what the negative cosine will look like, right? So when we get the reciprocal, when we're approaching this 0, when we're going -1 of cos of x as x approaches pi on 2 from, say, this side here, as we get closer and closer, this is becoming a bigger and bigger number because it's a reciprocal, right? If the denominator gets close to 0, then this blows up and gets really big. So we can sort of say that the general shape will be something like this for this quadrant here. We can say more about what it looks like specifically. So we're just going to maybe get rid of this part here. And we can find what, since this is our graph here, we can find at what value cos of pi gives us. We know that from our unit circle that at pi radians, this gives us -1. So therefore, when x is equal to pi, this gives -1. So -5 over -1 is simply just 5. This gives us this point here, and from our logic before, how the reciprocal will shoot up as we approach our asymptotes, it will look something, something like this, right? And this just keeps shooting up, getting infinitely closer. Now we need to figure out these parts here. So you can see as we get closer to this asymptote, it's purely negative. So we're going to get something like this. It's going to behave like that. It's going to shoot down. We just got to sort of find more information to get it more accurate. And the way that we can do that is by making use of the fact that the cosine is always going to be like 1 at the origin and at the end from the domain 0 to 2 pi. So we can plug in 0 here. This will give us 0 and well, cos of 0 is simply just 1, so -5. This is going to be the same for 2 pi. So these are the points that we're going to get here and here. Therefore, we can sort of connect this and see that it will behave in this way. Because making sure that it's a bit hard to draw on this, a lot easier on paper. But this should be the shape of the graph. Because if we compare this, say, in red with the negative cosine, like what we had before, it'll be something like this, and then down here, and then it goes like this here. Right, since this is negative, as this gets closer and closer, it should just start shooting down. But because we've got the starting condition of the point, then we can say it sort of looks like that. Obviously, this is just like an idea. It's still helpful, but it's not to scale, just because the reciprocal functions blow up pretty fast. Okay, so next question is going to be find the general solution for this guy here. So straight away, I'm thinking this is a little bit tricky. We're probably not going to get any tangents, because if I rewrite this as 3 cos of x, and I try and do this, right? If I divide both by cos, then I get root 3 is equal to secant plus tan, which isn't really, I don't really see anything useful with just these single degree functions, right? It's only useful when we have the squares that we can sort of use like our Pythagorean identities. So I'm thinking that maybe we have to use our angle sum formula. So maybe it can be the cos of, say, x. Well, we know that cos of a plus b is equal to the cos of a cos of b minus sine of a sine of b. So we can see here that it's sort of in the same form as this. So we get something like this, but I think that what we need to recognize is that we might get something nice if we rewrite this as root 3 on 2 cos of x minus 1/2 sine of x equals 1/2. So therefore we can say that, well, the at 30 degrees cosine is root 3 on 2 and the sine is also simultaneously 1/2. So we can say that cos of x plus pi on 6 is equal to root 3 on 2 cos of x minus 1/2 sine of x, because, well, this is just going to be cos of pi 6, which is root 3 on 2, cos of x minus sine of pi on 6, which is negative 1/2. So we get something like this, which is a really nice simplification. Therefore, cos of x plus pi on 6 is equal to 1/2. Therefore, we can write that x plus pi on 6, when is the cosine equal to a half? Well, a half is going to be here, right? In the horizontal, because it's a cosine. So we're gonna have these two angles here. So AST, yeah. So therefore, the cosine is a half at 60 degrees. So x plus pi on 6 is equal to pi on 3 plus 2k pi, because it repeats every revolution. And then we're also going to have x plus pi on 6 is equal to 2 pi minus pi on 3. So this is 6 pi on 3 minus pi on 3, which gives 5 pi on 3, is equal to 5 pi on 3 plus 2k pi. Therefore, we can rewrite this for x. X is equal to pi on 3 minus pi on 6. Well, this is 2 pi on 6. So 2 pi on 6 minus pi on 6 is just pi on 6 plus 2k pi. And it's also going to be equal to 5 pi on 3, take away 5. Wait, did I do that? Yeah, okay. So then this is going to be 10 pi on 6 minus pi on 6, which gives us 9 pi on 6. So 9 pi on 6 is 3/2 pi plus 2k pi. Yeah, maybe you can just write it like that. So I think that these where k is an integer, because these solutions repeat every revolution. So every time we go around, we get one of those. Yep. Okay. There's also another way that you can do this that I did want to spend a little bit of time speaking about. So let me just rewrite the problem. Okay, so what we can do is we can write this as root 3 cos of x is equal to 1 plus sine of x. This is going to be the same as 9 cos squared of x is equal to 1 plus 2 sine x plus sine squared x. But we know from our Pythagorean identity that cos squared is nothing more than 1 minus sine squared. Sorry, this should not be 9, this should just be 3, because it's the square root. 1 plus 2 sine x plus sine squared x. Now, this becomes 3 minus 3 sine squared x equals 1 plus 2 sine x plus sine squared x. So therefore we can set this equal to 0, and this gives us 4 sine squared x plus 2 sine x. 1 minus 3 minus 2 is equal to 0. So if we set sine of x equals to variable t, then we get 4t squared plus 2t minus 2 equals 0, which is entirely equivalent to 2t squared plus t minus 1 equals 0. So we can solve this. It's going to use a quadratic formula. So negative 1 plus or minus square root of 1 plus 8 over 4. So this is negative 1 plus or minus 3 over 4, which then gives us either negative 1 minus 3, negative 1, or negative 1 plus 3, which is negative 2, or, sorry, no, it's just 2 on 4, 1/2. So therefore, we get these solutions that sine of x is equal to negative 1, which corresponds to, like, because sine is the vertical, then this corresponds to only 3 pi on 2 plus 2k pi. Then we also get sine of x equaling 1/2, right? And this corresponds to these two solutions here, right? So this corresponds to pi on 6 plus 2k pi, and also 5 pi on 6 plus 2k pi. But before we only got 3 pi on 2 plus pi on and pi on 6. So what's up with this guy here? There's a really small subtlety when squaring equations, namely if you've got something like this, a is equal to 1, right, as one equation, and negative a is equal to 1, right? If you square both equations, you get a squared is equal to 1 and a squared is equal to 1. These, right, they look the same, but they came from different original equations. So it's just that when you square something, you sort of have to be careful that maybe there's a negative that isn't accounted for, or something that just, it doesn't tell you the full story. So you have to be a little bit more careful. I guess another way that you can visualize this is that in this equation here, a equals 1, I can rewrite this as a squared minus 1 equals 0. Using difference of squares, I know that this is just this, equals 0. And this gives me two equations, a minus 1 equals 0, which is a is equal to 1, or a plus 1 equals 0. A is equal to negative 1, right, where a is originally only 1. So that's why we sort of get an additional equation, an additional result, which may not necessarily be true. So we can just verify, well, we know from our previous question that 5 pi and 6 can't be the answer. So we can just chuck it in, like if we've got root 3 of cos of 5 pi on 6, well, we know that this is going to be like, yeah. So cos of 5 pi on 6, well, that is going to be negative root 3 on 2. So this just becomes negative root 3 on 2 minus the sine of 5 pi on 6, which is going to be 1/2 minus 1/2. We say that this is equal to 1. Well, this is simply going to be -3 on 2 minus 1/2, which is going to be -2, which is not equal to 1. So that's why we're just going to be careful. I guess another way you can sort of see it is that I think when you get up to, say, this step here, 3 cos squared of x is equal to 1 plus sine x, right? This is going to be the same as 3 cos squared. Right, I'm just going to rewrite it like this. But root 3 minus 1 plus sine x squared equals 0. Again, using difference by squares, this is 3 cos of x minus 1 plus sine of x times root 3 cos of x plus 1 plus sine x, right? And we want this equal to 0. We can see that only one of these is going to be our answer, namely this one here. This guy we want to neglect. So this equation here carries the additional unwanted solution. So it's just something to be careful of. I guess if you do something like this, you just have to double check your answers, which doesn't take long. But it is generally safer to try and avoid squaring these trigonometric equations, just because, yeah, you have extra work to do. And here, it's a little bit quicker. And once you sort of know what to look for, it's pretty easy. Or it's repetitive, I guess. Okay. Now we want to prove an identity. So to do this, just because I don't remember the tan angle identities, I'm just going to pull up the formula sheet. Okay. This one, so I did look at the formulas and it's a bit of a tricky one. So I believe that this question is actually a lot more difficult than you would normally get. Normally, a proof like this should be done in 2 steps, where you prove a intermediate result and then go off of that. So first, I'm just going to rewrite the left-hand side using the tan subtraction identity, which I have on my formula sheet, that this is going to be tan of theta minus 1 plus tan of theta, simply just because the tan of pi on 4 is 1. So that's why it simplifies down to this. This is just sine theta on cos theta. 1 can be written as cos theta over 1 plus sine theta cos theta. Again, here this can just be written as cos theta plus. So common denominator of cos gives us sine theta minus cos theta over cos theta plus sine theta. And so now we want to show that this is equal to this, which is a lot easier than showing that this goes into this, in my opinion. So now we go with right hand side and we say that this, well, we know that this is sine 2 theta minus 1. We know that this is precisely, well, on your formula sheet it gives it to you for free, but it's a very useful identity to know that, because, or to just be able to derive it on your own, I suppose. This is cos squared x minus sine squared x, where cos squared x is nothing more than 1 minus sine squared x. So therefore 1 minus 2 sine squared x is cos 2x. This is exactly what this denominator is. So this can just be cos of 2 theta. Okay. Now we know that this is going to be sine of 2 theta minus sine squared theta minus cos squared theta just by using the definition of 1. And we also know that cos of 2 theta is this here. Cos squared theta minus sine squared theta. I think maybe it might help to write it like this. Minus sine squared theta. So then, let me see. I think now we can sort of see that this here can be written as a square, because it's a square and a square plus, well, this here we know is 2 sine theta cos theta. So therefore, if we write this as -1 of sine squared theta minus 2 sine theta cos theta plus cos squared theta over this is denominator is a difference of squares, right? This is cos theta plus sine theta cos theta minus sine theta. So therefore this is just going to be negative of sine theta plus cosine theta over well, this here is cos theta plus sine theta cos theta minus sine theta. So therefore, this cancels with this, leaving us with -1 over cos theta minus sine theta. I guess you can see that we're almost there. Just got to show that this is this guy here. How to do that? We could multiply the denominator by the conjugate. So this is cos theta plus sine theta cos theta plus sine theta. This then gives us minus cos theta minus sine theta over cos squared theta minus sine squared theta. Okay. This here, sine theta minus cos theta minus, no, this is wrong. This should be a square. That's where I went wrong. Right. So then this cancels with that, and I'm left with 1 left. So I'm left with negative sine theta minus cos theta over cos theta minus sine theta. This is going to be the same as sine theta plus cos theta over sine theta minus cos theta, which I guess, what am I missing? I'm missing something. Sine theta. So this is, if you take the negative out, right, this is there. So that's 2 sine theta minus, that's there. That's good. That's good. So it's going to be minus times that, which is negative sine theta, negative cos theta. Cos theta minus sine theta plus cos theta. I made another error. This be a negative because this here is a negative there. So therefore, this is going to be a plus, which means that if I change this is a negative, then this is a plus, which is what we needed. It's a pretty difficult proof, but you can see we got there in the end. We just needed to do this intermediate result and then just a bit of algebra. Using a difference of squares is very important. All of that stuff. I think that's it for this calculator free section. A little bit difficult, but that's how it goes.